Hello everyone, welcome back to this NPTEL lecture series on cycloaddition reaction. In the last lecture, we talked about the utility of nitrones in 1,3-dipolar cycloaddition, and today we will talk about another dipole called carbonyl ylides and how these carbonyl ylides are used in 1,3-dipolar cycloaddition to give some interesting molecules. So what is carbonyl ylide? So when we talk about ylides are nothing but carbons having a negative charge attached to a heteroatom. So we all know very well about Wittig salt. So in Wittig salt it is phosphorus ylide. So along the line, if you want to know what is carbonyl ylides, you can see here you have a negative charge on the carbon which is attached to a carbonyl group, and here the carbonyl oxygen is having a positive charge. Okay, that is why this is called carbonyl ylides. How these carbonyl ylides are prepared? Are they stable? Because some of the Wittig ylides are stable. So likewise, whether carbonyl ylides are stable? No, they are not stable, they are very reactive. So that is why carbonyl ylides are prepared in situ and used as such in many 1,3-dipolar cycloaddition reaction. How these carbonyl ylides are prepared? There are many methods to prepare carbonyl ylides. For example, if you start with an epoxide and then if you slowly heat it, then this particular bond can undergo a heterolytic cleavage. So when it undergoes a heterolytic cleavage, what you get is this compound. So where one side you get a negative charge and the other side you get a positive charge. But this positive charge will be neutralized by the lone pair on the oxygen, and thus it leads to the formation of carbonyl ylide. So this can be generated in situ. What you can do is you can take this epoxide and then slowly heat it and then also add an alkene. See, for example, if you do this reaction in the presence of styrene, then this can undergo immediately after forming the carbonyl ylide, it can undergo 1,3-dipolar cycloaddition to form this tetrahydropyran ring. Likewise, you can take any epoxide. For example, if you take this epoxide, if it undergoes disrotatory ring opening, then you will get this carbonyl ylide, and it can also undergo a conrotatory ring opening. Okay, so when it undergoes conrotatory ring opening, you will get this ylide. Of course, if you have to do conrotatory opening, you should heat it, and if you have to do this rotatory ring opening, you have to shine light. Okay, under photochemical condition, you will have this ylide. And there are other ways to generate carbonyl ylides, but once you generate carbonyl ylides in situ, it can be easily trapped with various dipolar aphids. In this case, you can use maleic anhydride to trap the carbonyl ylide which is generated from this epoxide. Okay. So this is the ylide which is formed, and here also there are two possibilities, as you can see here. One possibility is the other possibility is but this is more favored mainly because the negative charge here is stabilized by the cyanide group. So that is why the heterolytic cleavage takes place in such a way that the negative charge goes to carbon bearing electron withdrawing cyanide. Okay. Another method to generate carbonyl ylide is if we have a diazo compound. Okay. So this is a diazo compound, and then if you use a transient metal like copper. So what happens? As soon as it forms carbene and this metal also gets attached, so we can call it as copper carbonyl. Okay, this copper carbonyl can immediately undergo a 1,3-dipolar cycloaddition with dimethyl fumarate. So the intermediate is this is a carbonyl ylide which is generated between this benzaldehyde and this diazo compound when you treat with copper, and that spontaneously undergoes 1,3-dipolar cycloaddition with dimethyl fumarate. There are other ways, as I discussed. Basically what you need is to generate a carbene. For example, if you take this simple 3-membered ring and then if you heat it, it can undergo immediately the loss of nitrogen to form a carbene. Once this carbene is formed, you can add any carbonyl group. For example, if you add acetone, and immediately it will form this carbonyl ylide. Once the carbonyl ylide is formed, then you can trap it with various dipolarophiles. For example, if you use dimethyl acetylene dicarboxylate, so it can form this 5-membered ring. So this is another very simple and interesting way to prepare carbonyl ylide. So if you look at this starting material and treat with any fluoride source, for example, if you use cesium fluoride, the fluoride can attack the trimethyl silyl group, and that can lead to the formation of negative charge here. At the same time, the lone pair on the oxygen can push the chlorine out. That way it generates a carbonyl ylide in situ, and that again can be trapped by dimethyl acetylene dicarboxylate to get this 5-membered ring. Well, as I said earlier, if you have a diazo compound, if you have a carbonyl group, then you can use a transition metal to generate the carbonyl ylide, and this carbonyl ylide can undergo a dipolar cycloaddition reaction with dipolarophiles. And here if we use excess benzaldehyde, the benzaldehyde itself will act as dipolarophile to undergo this 3+2 cycloaddition to form this benzylidene derivative. It's a very nice and interesting way to protect benzaldehyde. It's a different way. This is nothing but a benzaldehyde being protected by a diol. And in this particular case, if you have an enamine and then treat with any nitride, so what happens if you know whenever you have an aromatic amine, primary amine, if you treat with sodium nitrite and HCl, so it forms the corresponding diazonium salt. The diazonium salt, if you heat it, nitrogen will go and then you will get a carbene. So this is what happens when you treat with sodium nitrite or alkyl nitrite. So now this carbene, if you add acetone or any carbonyl group, immediately you will get this carbonyl ylide. And if you add excess acetone, because mostly when you use acetone is a solvent, so the excess acetone, the next acetone molecule will undergo 1,3-dipolar cycloaddition with this dipole derived in situ to form this interesting compound. Then, as I said, there are many methods to form carbonyl ylides. One of the methods is to use transition metal. A copper metal is routinely used, but when you use copper, normally to make this carbonyl ylide, you have to heat it. However, if you use rhodium, the same thing can be done at room temperature. Sometimes even you can do it at 0 degrees. So you take a diazo compound and then treat with any carbonyl compound in the presence of rhodium. So the standard rhodium catalyst used is dirhodium tetraacetate. So this dirhodium tetraacetate, when you have substrate like this, first it forms this carbonide, and this carbonide, as you can see here, this lone pair neutralizes the carbonide to generate this carbonyl ylide. Okay. So, once you have this carbonyl ylide, then you can trap it with various dipolarophiles. So, let us see. So, this dipole, this carbonyl ylide, if you treat with N-phenyl melamide, so it can give this very interesting cycloadduct. And if you look at this carefully, this is the exo product. As we have seen and as we have discussed in the case of 1,3-dipolar cycloaddition, due to lack of secondary orbital interaction, exo product is the major product. And same thing if you do with benzoquinone or naphthoquinone, you get this exo product as the major product. And if you treat with dimethylacetylene dicarboxylate, then you get this tricyclic compound. And one can also use carbonyl groups. For example, if you treat this with benzaldehyde, then you get this compound. Okay. So, basically the dipoles here, carbonyl ylides, can be generated in situ by mixing the corresponding carbonyl group with the diazo compound, and in the presence of various dipolarophile, the in situ generated carbonyl ylide can undergo 1,3-dipolar cycloaddition reaction to give corresponding cycloadducts. And if you look at this particular example, you can see here 1, 2, 3, 4, 5, 6. So, if you treat this with dirhodium tetraacetate, it should form a 6-membered carbonyl ylide, and once it is formed, then it can undergo 1,3-dipolar cycloaddition with dimethylacetylene dicarboxylate and N-phenyl melamide to give this polycyclic compounds. It's very easy. And this particular diazo compound was derived from camphenic acid. So, this is commercially available chiral compound, and if you treat with oxalyl chloride and diazomethane, you get this compound. Okay. So, once you have this, then if you treat with dirhodium tetraacetate, the ring size which will be formed is 5-membered ring. A 5-membered carbonyl ylide will be generated, and that immediately was trapped by benzaldehyde through 1,3-dipolar cycloaddition to get this tetracyclic compound. One can also use methyl propionate and other dipolarophiles to get the corresponding cycloadducts. It is a very simple straightforward reaction. One can also get a cyclopropane moiety, which is already present in the starting material, and this can be easily obtained from the corresponding carboxylic acid, and this can be obtained from ethyl acetoacetate. Okay. And this, upon treatment with dirhodium tetraacetate, it generates this carbonyl ylide, and the in situ generated carbonyl ylide can undergo 1,3-dipolar cycloaddition with various dipolarophiles, and here if it reacts with cyclopentenone or any cycloalkenone, so it can give this tetracyclic compound, and again this is an exo product, and the regioselectivity is fixed, stereoselectivity is fixed. So, this way one can get polycyclic compound through 1,3-dipolar cycloaddition reaction. See, this is another very simple example, and you can see here this can form a 6-membered carbonyl ylide. If you take this diazo compound and then treat with usual rhodium catalysts, and immediately it forms this 6-membered carbonyl ylide, which undergoes dipolar cycloaddition with various dipolarophiles, for example, vinyl acetate to give this bicyclic compound, with dimethylacetylene dicarboxylate to get this bicyclic, and with methyl acrylate to give this bicyclic compound. And you can see the regioselectivity, the electron donating and electron withdrawing nature of the functional groups attached to the double bond plays important role in the regiochemical outcome of 1,3-dipolar cycloaddition of carbonyl ylides. So, this is called isomunchones, and you can take this diazo compound, and in fact this is very easy to prepare. For example, if you have any lactam like this and then treat with diketene, and then straight away you get the corresponding ketamine. Now, if you treat with DBU and tosyl acide, so you get the diazo transfer product, that is the diazo compound. So, once you have this diazo compound, then upon treatment with dirhodium tetraacetate, it forms this carbonyl ylide, and once you have this carbonyl ylide, then you can do the dipolar cycloaddition with various dipolarophiles to get the corresponding cycloadducts. Can this be extended to intramolecular? Okay, it is intramolecular 1,3-dipolar cycloaddition. Okay, so for example, if you have a ketone, a diazo compound and the dipolarophile, all are in the same substrate. So, now when you treat this with dirhodium tetraacetate, it should generate this dipole, okay, that is carbonyl ylide. Once the carbonyl ylide is generated, this can undergo 1,3-dipolar cycloaddition with the double bond which is already attached at this carbon. So, that will adopt the chair-like conformation, and that will lead to this interesting tetracyclic compound. Okay. From one ring, here starting with one ring, now we have added 3 more rings in one step with formation of carbonyl ylide followed by 1,3-dipolar cycloaddition. You can introduce 3 rings in one step. Can this be extended further? Yes. See, for example, if you take this 6-membered enone, okay, now when you treat with base, it can generate anion and then it can form this enolate. And this type of enolate also has a lone pair on the oxygen that can push this acetate. When that happens, you get this oxoberyllium ion. Now, this also can be written like this. When you write this way, this is nothing but carbonyl ylide, isn't it? This carbonyl ylide, then it can undergo 1,3-dipolar cycloaddition with various dipolarophiles. For example, if it undergoes 1,3-dipolar cycloaddition with cis alkene, then you get this product. It's a bicyclic compound, and you can see here one is 5-membered ring, then the other one is 6-membered ring. And this has been extended in the total synthesis of 4-ball esters. For example, this starting material which is highly substituted with chiral centers. Now, this upon treatment with base like DBU, it generates this type of carbonyl ylide. And you can see here, this is the carbonyl ylide and this is the dipolarophile, and this can undergo an intramolecular 1,3-dipolar cycloaddition to form this tricyclic compound. So, this is a key reaction in the total synthesis of 4-ball esters, and you can see here this compound can be redrawn like this, okay. And this 7-membered ring comes from this 1,3-dipolar cycloaddition reaction. What we have done today is we discussed about the various methods of preparation of carbonyl ylides, a very important dipole in 1,3-dipolar cycloaddition, and after making this carbonyl ylides, this has been successfully used in various 1,3-dipolar cycloaddition reactions. These carbonyl ylides are not stable, so they are always prepared in situ when they are prepared in situ, generally the dipolarophiles also were added to the reaction mixture, so that as soon as the carbonyl ylides are generated, it undergoes 1,3-dipolar cycloaddition to form the corresponding 1,3-dipolar cycloaddites. So next class what we will do, we will talk about nitrile oxides and azomethane ylides, which is a continuation of carbonyl ylides. Then we will move to azides in 1,3-dipolar cycloaddition reaction. Okay, so thank you.